So hello everyone, this is lecture 18 for the classical physics. In the last lecture we were discussing about the Lagrangian, we started that. So please pay attention, today's lecture is gonna be a little bit confusing, but it is very interesting. So we will start with degree of freedom. So what are degree of freedom in the classical mechanics? See here the independent set of variables means a particle is moving or in a motion, it is there. So the number of amount of variables we need to describe its motion, okay, and that variables should be independent of each other. So that is called the degree of freedom, means the minimum number of independent set of variables required to describe the motion of a particle. That is called the degree of freedom and independent variables. Okay, just like we were discussing some cases like pendulum and all. So there were x, y and z coordinates. So these three axes are independent of each other and we can describe the motion along them, but there were some constant involved then they were reduced the variables and all. So these x, y, z axes are independent axes and the degree of freedom are 3 for any particle exist. Okay, so which is free particle, so we have 3 independent axes and then hence the degree of freedom will be 3. So that's how you can define that. But there are complex systems, means if there are 3 and 4 system, 4 particles, then they have 5 particles will have 15 coordinates, independent coordinates. So it will becoming complex with more number of particles in the system. So let's see how we define the independent variables. So by this equation we can define that C1 du1 plus C2 du2 C3 du3 means these u1 u2 u3 are independent sets, okay, independent set of variables. Now these C are constants. So if this equation is like that, means this is equal to 0, then these all coefficients should be equal to 0. Only then we can say that u1 u2 u3 and all are independent of each other. Okay, so this is a linear independent, you know about this from mathematical physics. See, if we say that C2 C3 sorry C2 C4 and C7 are not 0, then what happen? See, if these are not 0, then you can write u4 u7 in terms of u2 u4 in terms of u2 u7, means they will be independent on each other, and this is not the definition of independent variables. That's why these all should be equal to 0. Only then we can say that these are the independent variables, and these are nothing but degree of freedoms, means the number of amount of independent variables required to define the motion of a particle is degree of freedom, and these are the independent variables. So what is the use of these in degree of freedoms and the independent variables here? See, if you see the 3D system we have, then each particle is described by 3 coordinates. So if there are n particles, then they will be described by 3n Cartesian coordinates. So you will have q1 q2 q3 qn forget this, you have 3n Cartesian coordinates. So it will be a very complex system. Now see, there will be some constants in the system, they will reduce these coordinates, means if there are k constant, then it will be reduced by 3n minus k, we will see about this. Now see, if these coordinates are reduced, means they are become 3n minus k, but still they are very large, means if you represent them in this 3D axis, then this will be a very complex system, means this will be trajectory for 1 2 3 4 5 and all. So if there are many numbers, then they will be very messy here. So see, if we introduce how much number of independent coordinates we are having, so we will introduce that amount of dimensions, means if we have 5 independent variables, then we will introduce 5 dimension here, means in the real space we have only 3, so let's introduce the 5 dimensions, means the 5 independent axes and perpendicular to each other. Then we can define that whole system with the help of only one single point. Okay, so that is what we gonna do here. So not try to imagine this, because this is a imaginary thing. Okay, so we will just know that we will introduce n amount of axes, means any number of free degree of freedoms we have, we will introduce that much or that number of independent axes, and that space is called the configurational space. Now if you are having 3n coordinates and using the k constants, you will get 3n minus k degree of freedoms. So 3n minus k will be equal to small n, and then there will be small n amount of independent axes we need. So with the independent variables will be q1 q2 and q1. So these number of independent variables can be represented with n axis system, means now we will introduce n axis, and any single point can represent all these coordinates. So now we don't need this massive system, only a single point can represent all these motion. Okay, so n particles can be represented by single point in the configurational space. And like this, you can represent this point at this, means at any time any system can be represented by a single point. Now with time it is moving, then whole system is moving with time, then this single line can denote the whole path or whole the process it is going under to reach the second coordinate. Means system is going from one position to another, then this single line can represent the whole evolution of that system. Okay, so we don't need the n, means now we are having n dimension systems, small n dimension. So you will see about it when we discuss more about the particles and examples. So at any time we will have small n coordinates here. Just remember this, because the 3-axis system, 3D system, we are giving us the 3 coordinates. Now n-axis system will give us n coordinates. So for the n independent axis we have single point. So that's how this is making us making things easy for us. So let's see. Degree of freedom of a free particle is 3. Single particle can be represented by these 3 independent coordinates x, y, z. Now if there are n free particles, means this was only one. If n free particles we have, then total coordinates required will be 3n. So degree of freedom will be 3n. Now if there are k constants involved, n number of particles with k constants, so we know that constants reduce the number of variables, we already see that. So 3n minus k will be the net number of degree of freedoms required. Okay, so this will be like this. It means we are thinking that each constant reduce one of the variable. So this will be our total degree of freedoms. So let's see one example. Let's see, we have simple pendulum, and it is like the pendulum, okay, oscillating about it from this is the wall. So this bob, this length is fixed, so one of the constant is x square plus y square equal to l square, we know this, and it is moving in the xy plane only, so z will be 0, so this will be your second constant. Now you have two constant here, and coordinates involved with the bob is 3, because x, y, z can denote the motion of this. So and bob is only 1, so we will use this formula, 3 into 1 minus 2 constants, it will give you 1. So only one independent variable required to describe whole the motion of this pendulum, and we already see that, means this is equal to 0, and y square can be written as l square minus x square. So with the help of x only you can find y, and z is already you know. So that's how only one independent variable is required. So that's how you can use this formula. Let's see for different systems. For a spherical pendulum, you know what is a spherical pendulum, means a bob is independent to move on a surface of the sphere, okay, and this length will be fixed. So see, this length is nothing but xyz minus 0, so it will be x square plus y square plus z square equal to l square. So we denote this length as r, so r will be l, this will be your one of the constant, and there will be only this one constant. So total degree of freedom will be 3n, n is 1, 3 minus 1 will give you 2. So two independent variables are required to describe the motion of this bob. See, this theta and phi angle we know in the spherical coordinate system, we have these r, theta, phi. So r is fixed, then theta, phi can be varied. So only two variables are there, so that's how you can find that this will be same, the 2. Now let's see the conical pendulum. What is the conical pendulum? Means the particle is free to rotate around in a cone, okay. So see, this angle will be fixed, so this angle make this angle fixed. So this is one of your constant, and this length is fixed, so this is your another constant. So you have two constant and one particle, so total degree of freedom will be 1. So with the help of one single variable you can define whole the motion of the system. Now we see the dumbbell. What is dumbbell? There are two masses associated, and the length is L0, and this system is free to move in the space. Then what is the constant here? This length is only constant, means this length will remain fixed. So there are two particles, so three coordinates are associated with it, 3 with it. So 3 to the 6 minus 1 will give you 5. So 5 independent variables required to describe the motion of this. See, this is the equation. Means x1, y1, z1 are coordinates of this, x2, y2, z2 will be this, then x2 minus this length will be equal to L square. So this denotes the length. Now see, this will reduce one of the variable, this equation. But what if say that this is dumbbell is restricted to move in a plane only, means only xy plane, it can't move in the z plane, then what? This dumbbell is restricted to move on a surface, z1 equal to 0, z2 equal to 0, means now with the surface it can't move to the upside, so z1 and z2 will be 0. So see, we have introduced two more constant, that is z1 equal to 0, z2 equal to 0. So it will give you, these will be 0, so you will have 4 variables here and L0 square. So according to the formula, 2 plus 1, 3 constant will give you 3 to the 6 minus 3, 3 to the 6 minus 3 will give you 3 degree of freedoms. Now from here you can see that when these will be 0, there will be 4 variable and one of the variable can be written in the form of other 3. So from here also you can see that only 3 independent variables are required. So that's how you can see that how net variables can be reduced using the constant equations. Let's see one more example. 3 masses connected by 3 rigid massless rods. So these 3 masses are connected with these rods and these are massless. So with it 3 coordinates associated, with it 3. So 3 multiplied by 3 will give you 9, minus 3 constants are there. So 9 minus 3 will give you 6 degree of freedoms. Because these lengths are fixed, so they act as a constant. So 3 constants you have. Now a rigid system. What is a rigid system? A body is said to be a rigid body if relative separation between any two of its parts is always fixed. Means the distance between any 2 points you take, that will always remain fixed, whether it is moving in the rotational motion or translational motion, in any kind of motion it can be, but this distance will always remain fixed between 2 points. So that is a rigid body. So let's see the degree of freedom for a rigid body. So if you have only 2 particles and you are seeing the degree of freedom for them, then this length will be fixed, so only one constant you have, that is distance r. So it will give you 3 to the 6 minus 1, 5 degree of freedoms. But what if there is 3 particles involved, means you have these 2 and this third is also. Now you have 3 constants, this length and this length. So 3 3 and 9 minus 3 will give you 6 degree of freedom for this, because these r1 2 r2 3 and r3 1 will be fixed. So these are the degree of freedoms. What if, now this is the interesting thing, what if you have one more one more constant, means one more particle, then for this 4 particle system, what is the number of degree of freedoms? So it will be 3 4 12 minus, now see 3 are involved with this already, with coming this it will be 1 2 3 more constants, so it will give you 3 4 12 minus 6, this will give you 6 again. Now let's say one more particle is there, so it will also give you 3 again, okay, means 3 because of this, so 6 is already there and 3 with this 9, so you will get 6 again. So what you are seeing here, that degree of freedom is always remaining 6. And why is that? Because after 3 particles any 4th particle can be find, means if you take this particle, the coordinates of this point can be find it using these 3, means because this length is fixed, this length is fixed and this length is fixed. So, and you have that's how you have 3 equations and only 3 variables with this associated. So using 3 equations you can find these 3 variables easily. That's why they are not independent, only means they will repeat after itself, means for this point also you can find the coordinates using these points, for this also you can find coordinates using these points. Any number of particles will give you coordinates you only using these 3 points. So whatever degree of freedom you are having with these 3 points, that will be all. So that will be 6. So you see, you are finding 6 always degree of freedoms. So it will be 6 for a rigid body. So remember this. So out of these 6 independent variables, 3 are attached with, now in these 6 independent variables, 3 are attached with center of mass to describe the translational motion. So 3 are associated with the center of mass, this whole system. And rest 3 are used to describe the rotation of the rigid body. These 3 variables are called the Euler's angle. So we get that in the rigid system we have only the 6 independent variables. In that the 3 variables are associated with the center of mass to describe its translational motion, and other 3 are associated with the rotational motion of that system. So that's how we describe the 6 independent variables for a rigid body. Now degree of freedom for a rigid body fixed at one point. Now this point is fixed, it can't move anywhere. Okay, so what is the degree of freedom for this system? So see, x1 will be fixed for this, x2 will be fixed, and x1, y1, z1 fixed for this. Means these 3 coordinates are fixed, they are not going to change. So they will give us 3 restraints or the constants. So x1, x0, y1, y0, z1, z0 are constants. And if you take any 2 points, means 3 points are required actually to get the idea. So this distance will be fixed, this distance will be fixed, and this distance will be fixed. So 3 constant from here and 3 constant from here. So you will total have 6 constants, and it will give you 3, 3, 9 minus 6. So 3 degree of freedoms are available. Only 3 degree of freedoms are required to describe the motion of a rigid body fixed at one point. Now let's see one more example. This is a table, and there is this hole and a mass is attached, and it is free to rotate on the surface, and there is a mass which is hanging down the table, m2. So, and the length of the whole string is L0. m2 can move only in the vertical direction, m1 can move only on this surface. So we have to find the degree of freedom for this system. See, this system will be constant to move in the z axis only. So there will be one constant because of this, and this one can't move in the vertical and the downward direction. So z will be 0 for this, and x1, y1 will be depending on the theta only. You can find r cos theta will give you x1 for this, and r sin theta will give you y1 for this. So you will have only constant here is x1 z1 equal to 0 for this one, and for this one x2 y2 will be 0 because z is it is moving in the z direction. So x2 y2 will be 0 for m2. And what is the z2? So z2 will always remain same, that is this complete length minus r. So this r can be anything, so this will always remain fixed, L0 minus r, z2 will be this. So only 4 constants you have in this system, and there are 2 particles, so it will be 3 to the 6 minus 4, it will give you 2 degree of freedoms. So only 2 independent variables are required to describe this whole system. Now let's see the last for today. That is, we have this spring system, m1 and m2 are attached with it. So what is the degree of freedom for this? Now see that spring is introducing a constant because it is binding 2 masses together. So because of this spring we have these 2 masses, they can't move, means they can move but they are always remain together, and length will change with time. So see, this is the kind of example of that constant which can't reduce the variable for these 2 systems. Spring is introducing a constant because it is binding 2 masses together. They are not free to move away from each other because of the spring. They will somewhere gonna stop. So, however, the constant does not have the ability to reduce one of the independent variable because length of the spring is not constant. Length is not fixed. So that's why they will not able to reduce the variables. So you will have 3 for this, 3 for this. So your total degree of freedom will be 6 for this kind of system always. Okay. And this is a holonomic constant which is time dependent. Okay. So that's it. This is there is some this kind of example also where they have no ability to reduce the independent variable. So remember this. Now why I am telling you all these. So now you have degree of freedoms for all kind of systems I told you. So that number of independent axes you need. So you will have 6D system, 6 dimension, here 2 dimension system you will have. So the number of degree of freedom will give you number of axes required to describe the motion of the system. So you will have that much, and then only single point will give you the position or the system's situation at that point. So we'll see more about it in the next lecture. So if you are still having any doubt, then put it in the comment section. I will try to resolve. Thank you everyone.